sledder goes down a snowy hill with an incline of 10 degrees relative to the horizontal that has a kinetic coefficient of friction of 0.035, which is pretty small but might make sense for a nice slippery snowy hill, or maybe it's kind of icy. Calculate the sledder's acceleration. Compare this to the acceleration if there had been no friction. Well, I'm going to focus first on just doing the acceleration for this part here. So let me do a quick picture here of like a sledder. I'm not sure if my picture is necessarily going to be the same as your picture, but I'm just going to like, here it is. Here's like a person. Okay, that's good enough for me. There's a sledder. That's probably enough for me to draw an FBD. I want to leave maybe enough space for my FBD, so I'm going to start it kind of way out here. Hopefully that's good enough. So it makes sense maybe to start with gravity, have that in there. There's going to be a normal force that's going to be at an angle. And there's going to be a super tiny, although I don't know if I can draw it tiny enough to reflect. Why do I think it's tiny? Well, that coefficient of friction is so tiny that I believe this force of friction must be tiny. I'm not sure if my picture does its tininess justice because I needed to get enough of it in there to at least see which direction it's pointing, see how it's at right angles with the normal force. I wanted to at least convey that. Let me also state somewhere that I think the direction of acceleration, maybe I'll put that in the picture here, I think it's pretty clear that the acceleration is down the hill like this, because that's going to help me to make some decisions. So my goal is to find acceleration, so naturally I think I'd want to use Newton's second law. F net equals mass times acceleration. And seeing the forces that I have here, I'm going to go ahead and write, I'll start with the normal force this time. Normal force plus force of gravity plus that force of friction. So this is really the vector equation I'm going to be working with. And these are the pictures that kind of describe the vectors that are in that vector equation. So then the question might be, well, how am I going to proceed from here? I think there's enough vectors here. I don't want to do geometry. I think I'm going to do components. But a lot of these are kind of rotated away from like what might be a more normal XY Cartesian coordinate system. So I feel like it might not be a half bad idea to use a rotated coordinate system. So I'm just going to draw in here in between, just for reference again, an X and a Y coordinate system to indicate I'm using a rotated coordinate system. So that means really the acceleration, even though it's down the hill and not actually horizontal, is aligned with the X direction, is in the positive X direction. And then I'm going to proceed with a component-based analysis for this. And I think this one's complicated enough. I might want to do both X and Y components on this one. So looking at the X components, normal force, I don't think there is one. How do I do gravity? That's a tough sounding one right there. Maybe to help me out with that, I'm just going to take my gravity vector and I'm going to draw a copy of it over here and kind of hang it from my coordinate system to help me figure this out. And let me see. Recognize that when I have this angle of incline, I haven't put that in my picture yet, but really that angle represents this angle right here. So maybe I can say, okay, that's that 10 degrees that I was given, and I think it's pretty clear that that's going to be a 10 degree right here. And then if I look at the components of this gravity vector, there is a component in the X direction, there's a component in the Y direction, and I choose it, it's getting a little muddled there, but that same 10 degrees is right there, kind of the smaller angle in that right triangle. And the X component is opposite to that. So I apologize, I don't have a lot of space here to show all of this, but the opposite tells me enough to say that whatever the gravitational force's magnitude is, it's going to be in the X direction is going to be related to the sine of the angle. And it's positive because X and is in the same direction as this component points. Otherwise, I'd put a minus sign here. Force of friction, I think, is in the negative X direction, so I'm going to throw that in as a minus F sub F. And then acceleration is in the positive X direction, so I'm going to put that as an MA on the right side of this component equation. And again, that was using this as a guide and all the pictures to help me figure out the parts, and the normal force didn't contribute anything at all. But now looking at the Y's, the normal force definitely contributes something there. It's pointing in the positive Y direction, so I think it makes sense to put that in there. I think the only other part is that this gravitational force has a component that is pointing in the negative y direction. You know, maybe, I don't know, maybe I can recopy that real quickly here. Like the part that I'm looking at here is I'm saying, hey, if this is f sub g, here was kind of the x component, here is the y component, here is that 10 degrees. So again, this is like f sub g sub x, this is f sub g sub y, but again, since y is kind of pointing in this sort of slanted upward direction, I think, let's make that a clear f there. I think f sub g sub y should be a minus fg, and it's adjacent to the angle 10. Oops, I put it as a theta here. Hopefully everyone's cool with that. I'm going to put that as a theta here as well, but we'll remember, I'll record somewhere that theta really is equal to 10 degrees. For some reason, that's my habit to do that. So there it is. And then I can set that equal to 0 because clearly acceleration is only in the x direction in my rotated coordinate system. Now, before I move on to doing too much math, one of the things that I was taught at some point was to try to finish all your physics reasoning before you start monkeying around with the math. So I'd like to include one more thing here, because we do have that coefficient of friction, and this is kinetic friction. So I think the force of friction can be related through that coefficient to the normal force. And now I can really say, okay, physics is done. What am I going to do with it? All right, well, let me start with this equation down here. I think I can solve for the normal force. Why might I do that? Well, if I solve the normal force, I could put that in here and get something for friction force, and then I could put that in here and maybe do something with it. That's kind of my rough plan. We'll see if it works or if it doesn't. Anyway, I'm going to say that normal force is if I add fg cosine theta to both sides, or really that's cosine of 10 degrees, right? That's going to look like this. But then remember that f sub g is actually equal to just mg. So I'm going to put that in as an mg cosine theta for f sub n. So that really implies over here that the force of friction is equal to coefficient of friction times mg cosine of, and again, I'm putting theta just because it's easier for me to write than 10 degrees. I've decided to go with that. All right, now I can take that expression and go back into my first expression here. And maybe what I'll do is I'm going to rewrite this one cleanly. I'm going to include the fact that I've noted f sub g is just really equal to mg. So I'm going to say mg sine theta. So that's that term right there. Minus, and now for this one, I'm substituting in this monstrosity, which is mu sub k mg cosine theta is equal to ma. And what's really cool here is I didn't make note of this, and I didn't hear anyone complain, but then again, I'm doing a video here by myself, that I didn't give you the mass of the sledder and her sled. But I didn't need to, because mass actually cancels out here. I had to get pretty deep into the analysis, though, to see that, but that's not uncommon in these kinds of situations, so that's pretty cool. The other thing that's kind of popped out of this, though, is like, I think I can just write a solution for acceleration, which is what I was asked for in the first place, because what remains here is just equal to a. So I'm going to say a is equal, it looks like there's a common factor of g here, so I'm going to simplify to g multiplied by sine theta. So again, that's coming from there. Then it was minus mu sub k g, the cosine theta, but I'm factoring out the g, so I'm just going to make that a minus mu sub k cosine theta. There it is. And this is something that now I think I could go into my calculator and put in like 9.81 meters per second squared multiplied by the sine of 10 degrees minus 0.035 times the cosine of 10 degrees. And if I go and consult what my calculator says, it said 1.36535, etc. So let me see. I think that would round up to like 1.37. So I'm going to write that as 1.37. And that's meters per second squared, since the only units that are there came from the 9.81 meters per second squared in the g. So that answers the first part of this question. Then it says compare this to if there had been no friction. Well, maybe a simple way to do that is to recognize, oh, just knock away this term, set mu sub k equal to 0. But it turns out without friction, a is equal to g sine theta as a result that we saw before. So for the no friction part, I'm just going to say A is equal to G sine theta. I'm running a little bit out of space here, so I'm just going to put in my calculator the 9.81 times sine of 10 degrees, and then my calculator says that that is like it's like 1 point. Hang on, I lost the number here, but I think it's like 1.70. Let's just check the answer, see if I did that correctly or not. So, whoops, get my window here. There it is. We have the two numbers that we arrived at.